Hi guys, and welcome to this video today on Pythagoras Theorem. If you are watching it on YouTube, if you can do me the honor of clicking subscribe if you haven't already done so, and like this video and that little bell notifications, you'll get told when all of my new videos upload. If you are watching on maffsguru.com, welcome, thank you so much. And if you are not watching on maffsguru.com, head on over there, it's free, and all of these videos are searchable. They're all listed in a much more logical order than I could ever do here on YouTube. They are time-coded, there is exam questions, there is downloadable notes. There is so much more for you to actually experience. But let's get into this now. So Pythagoras Theorem, you have been doing this since you were practically in nappies. Maybe not that early, because that would be awesomely weird, but you've done Pythag, and by the end of this video, we're just going to recap what Pythag is, know that it applies to right angle triangles, know that it helps us find missing side lengths when we've got two sides, and also know what Pythagorean triads are, and not the scary ones that are in organized crime. Now, we've been dealing with this further maths video with all sorts of things like parallel lines and triangles and polygons, and we're just going to keep powering through all of this pre-knowledge, so when we get to things a little bit later in the course, you will absolutely ace this stuff. But let's recap Pythagoras Theorem using a diagram. Now, I don't know about you, but lots of people go, well, okay, Pythagoras Theorem is c squared equals a squared plus b squared. Just remember the formula and deal with it. But do they ever really explain where it came from? Now, you may be sitting there going, well, I don't really care. Fair enough. There are time codes below. If you want to, you can skip this section of the video. But I know that having taught it lots and lots of times now, when people understand what we're actually doing, they never get these questions wrong. So 2 more minutes of your time and we'll do that. Now, if you're anywhere else in the world, outside of Australia, you probably use the formula a squared equals b squared plus c squared, which to me makes a lot more sense because A, B, C, and I now want to burst into song with the Jackson 5, A, B, C. No, don't do it. Fight it, Mass Guru. Do not sing. But obviously, knowing where this formula comes from is maybe not really relevant. Who knows? I'm going to have a go, though, hopefully making it relevant to you. So we need to look at the following three squares. There is one square, there is a slightly bigger square, and there is, theoretically speaking, a much bigger square. Now, we don't currently know they are squares, so I'm going to put these little marks on the side. One little mark there, 2 little marks here, and 3 little marks here. Yeah. And that now tells me that these shapes, although they don't look like it, are in fact squares. And what do I need? I need some side lengths. So let's make that 3, and let's make that 4, and let's make that 5. Now, I'm not so much bothered about units at this moment in time. The point of it is 3, 4, 5 triangle. 3, 4, 5 is the dimensions of my squares. Now, what Pythagoras, and I'm not convinced there, because apparently he may have stolen, allegedly he may have stolen a lot of this. It may not even have been his theorem. But let's say Pythagoras realized that for certain squares, when you put them together in a particular order, what you found was their points joined to make a right angle triangle. Now, to us that seems fairly obvious, but can you imagine sitting around one day just playing with squares and putting all this together and finding this rule? Now, so what it said was, and I'm going to draw the triangle first. They said, well, if you put one square here and another square here, and generally these were the two smaller squares, and the much larger square here, that what you found was that this triangle here was in fact right angled. Now, has that got anything to do with Pythagoras' theorem? Okay, right. Well, let's at the moment think, so what did we say? This was 3, this was 4, and that was 5. So all of these sides were 5, and that was 4 and 4 and 4 and 3 and 3 and 3 and 5 and 5. Now, generally speaking, when we see squares, we're always interested in two things, yes? Area and perimeter. Well, what we're going to do is we're actually going to look at the areas of each of those squares. So remember we had 1, 2, 3 squares. This was 3, 4, and 5. So let's draw that triangle again. Here is my triangle. That's a really ropey triangle. There is my big square. There is another square. And here is another square. Let's just get rid of that line there and make this more like a square. Right, so what I'm going to do now is I'm going to write on the dimensions of the square, but just on the sides of the triangle. So that's 5, and that's 3, and that's 4. So what we now know is that this big square here has 5, 5, 5, 5 all the way around it. You know, the other squares have 3 and then 4. So I'm now going to work out the area of each of these squares. Well, we know what the area of a square is. It's base times height. And so 5 times 5 gives me 25. So I'm now going to write in here that this has an area of 25 units squared. Here, this square has got an area of 9 units squared, and this square here has an area of 4 by 4, 4 times 4, which is 16 units squared. Now, the question is, can you see what I'm trying to get you towards? What do you notice about the areas? Well, if we took 9 and added it to the 16, we get 25. So what that was trying to tell us was the area of this square added to the area of that square there gave me this square here for particular sets of squares. And for particular sets of squares where that happened, where the areas of the two smaller squares added together to give me the area of the bigger square, then we had a right angle triangle. Okay, so let's go back and let's just draw our triangle again, but I'm not going to put the squares on this time. So what I'm going to say is, well, this we said was 3, this was 4, and that was 5. And how did we find the area? We went 3 times 3, which we can write simpler as 3 squared. 4 times 4 was 4 squared, and 5 times 5 is 5 squared. And what did we do together to get the area? We did 3 squared plus 4 squared equals 5 squared. And ladies and gentlemen, hopefully by now you're like, so this has everything to do with areas. And yes, then we ended up with Pythagoras going, well, okay, let's make this not just about 3, 4, 5 triangles. Let's make this about letters, because they loved letters. And so what we ended up with was, here is my triangle. And what they said was, well, let's give each of these sides a letter. And we can call this A, and we can call this B, and let's call that C. And when that happened, what did we end up with as our formula? Well, if you remember, if it was a right angle triangle, we knew that B squared, A squared, and C squared looked at the areas of each of the squares that theoretically made up that side length. And as such, we knew that the smaller two sides added together would be equal to the area of the longer side. And for information, ladies and gentlemen, the longer side of a triangle is always called the hypotenuse. And there we go. That is where Pythagoras' theorem came from. And then the learnings just kept coming. Now, obviously, this photo here is of, well, I just went into Google and I went, triad. And obviously, these two guys were suggested as maybe being in some sort of a triad, which is a very dangerous and very scary organization with tattoos. Now, I just look at those tattoos going, ouch. Yeah, not one for paying me. Bang my thumb with my, if I'm doing DIY and I bang my thumb, I'm on the floor, literally, and then passed out. Can't do pain, thankfully never going to have a baby. But obviously, do all squares meet to make a right angle triangle? Sadly not, no. But there are a number of special ones that we use in mathematics, and they are called triads. And obviously there's 3 that we tend to use the most. And this one here is one of my ones I use in my example, which was the 3, 4, 5 triangle. We use this other one here, which is a 5, 12, 13 triangle. And another one I use, or I see ever such a lot, is the 9, 40, 41. Now again, when we have this, if I was to draw my right angle triangle, when we have the 9, 40, 41, can I write 9, 40 and 41 there? No, I can't. Why? Because the longest side has to have, or the slanty side, or this hypotenuse here has to be the longest. So that would be 41, and that would be 9. And I suppose the next question that people say to me is, well, do they have to be written in that order? No, because again, when we do, say, 3 plus 4, is that the same as 4 plus 3? Absolutely. So my triangle could just as equally been written as 41 has to be the longest, but 40 here and 9 there. And remember, this only applies to right-angled triangles. Okay, have we got this? I think we have. Now, I just want to highlight the fact that in exams, we use these 3, 4, 5s and 5, 12, 13 triangles a lot to try and trick you. And for example, here is a ladder leaning against a wall, and there is a wall, and there is my ground, and it's supposed to be flat, but this, never mind, can't do it. And what they'll say is, the ladder is 5 meters long, and it is resting 3 meters away from a vertical wall. What must the height be from the ground that the ladder reaches? And it's realistically saying, what is this height here? And lots of people go, oh, this is Pythagoras Theorem, I remember, and they go c squared equals a squared plus b squared, and they do all that working out. And I'm like, it's a trick. Because what do we notice? We've got a 5, we've got a 3, and they've told us it's a right angle triangle. So if I remember there's such a thing as a 3, 4, 5 triangle, I can automatically write down that the height above the ground of that would have to be 4. We are very fortunate here with mathsguru.com to be able to have a relationship with Cambridge, the phenomenal publisher, who have very kindly allowed me to use all of their worked examples, making these relevant. If you haven't got the Cambridge Essentials textbook, or the Cambridge Further Maths textbook, sorry, it is freaking awesome. Lots of examples, lots of great theory, and lots of questions. So we're going to do this now. The following examples, as I say, are used from permission. And example 1 says, find the value correct to 2 decimal places. Now, the minute I see 2 decimal places, I'm like, yay, I get to use my calculator. Of the unknown length of the triangle opposite. Now, the first thing we need to remember is the longest side is the thing that becomes the C. So I'm going to write down, firstly, always write down your formula. C squared equals a squared plus b squared. I know in some exams, particularly in the United Kingdom, you get 1 mark for writing a formula down, and I think that's awesome. All right, it's giving you marks for remembering the theory, which is what this is all about. So what is the value of c? Here we have x. So where I see a c, I'm going to write x squared is equal to a squared plus b squared. Now obviously we said a and b are these side lengths here, and they can be written in any order. So I'm just going to write 5.3 squared plus 6.1 squared. Now, I can't do this in my head. So, loading up my trusty calculator, let's work out 5.3 squared, and let's work out 6.1 squared. And there we go, we get 28.09 and 37.21. So, 28.09 plus 37.21. So we know x squared, adding those back together. So let's do this, plus this. And then we get 65.3. So there we go, 65.3. Is that my length of x? No, it is not, because if you remember, that's the value of x squared. So to get rid of that squared, we have to square root that side. And so thankfully my calculator has that as a function as well. So when I now go keyboard and square root, and let's copy in my answer. Oops, let's not copy my answer. Let's type it, 65.3, it's not a long one to go. We get 8.08. It's got to be correct to 2 decimal places. So 8.08, and there we go. We'd have to write our units of centimeters, and we're done. Now, that's the long way of doing it. The great thing about CAS calculators, and we use CAS calculators over here in Australia, is that there is something called the solve function. So I can actually go solve, and I can put that formula in. So I can say x squared is equal to 5.3 squared plus 6.1 squared, comma, x. Now the comma and the x basically says to the calculator, can you solve this please for x? And I've got my whole formula in, and I hit enter, and piff puff poof, out comes, hold on, what do we see? We see x equals minus 8.08 and x equals 8.08. So it's actually giving me 2 answers. And for square roots, we would normally expect 2 answers. Whole new discussion there. But because we can't have a negative side length, because we're trying to find the value of x, and we can't have a minus 8 centimeters. I mean, what does that even mean? It doesn't mean anything. We would actually ignore one of those answers, the negative one, and I would just look at x equals 8.08, which just so happens to be the value that we'd already got. So calculators are awesome, so long as we understand what it is they're trying to tell us. Okie dokie, here we go. Example 2, find the value correct to 2 decimal places. Also, I'm going to use my calculator for the unknown length of the triangle. Now, in this situation, what do you notice? They're giving you the hypotenuse. Now, the formula doesn't change. We still write c squared equals a squared plus b squared. So we know that c squared, we know that c in this case is 8.6 squared is equal to a. Now, I don't know the value of a. It says let it be y. So let's say y squared plus the value of b squared, which is 5.6 squared. Now I'm going to do it the long way around again by, yes, moving things around. Now I know that a plus 5.6 can be moved to the other side. And so I get 8.6 squared minus 5.6 squared is equal to y squared. And yes, firing up my trusty calculator, let's clear all that stuff down so that we can actually see. We'll turn off the calculator, and we've got 8.6 squared minus 5.6 squared gives me 42.6. So we get y squared is equal to 42.6. So y is the square root of 42.6, and I can't work that out in my head. So let's work out, please, if you will bring my calculator back, the square root. Let's see if I can actually copy this in this time in the right place. I can. And it gives me 6.526, but we've got to do it to 2 decimal places. So I need to look at that third decimal place. 6.53. Okay, so 6.53. What's the units? Centimeters again. But because we can, let's just check to see what happens if I use my solve function. Now again, we can just type in the equation as it is. So 8.6 squared equals y squared. Well, we've got a y on my calculator, plus 5.6 squared. We have to do the comma and tell it that this time we're going to solve for y, because that's my unknown variable, my pronumeral. Close my set of brackets, press equals, and poof, out comes those 2 answers again. Remember, we have to look at that calculator and go, well, which one makes sense? Well, a negative length of 6.52 or 6.53 doesn't make any sense. We're going to ignore that first one. And again, 6.53. And here is our last example. The diagonal of a soccer ground is 130 meters. Now, what you notice in this question is they have not given me a diagram. So, if all else fails, draw my own diagram. So there we go. I know soccer fields are rectangular, and it says the diagonal is 130 meters. So there is my diagonal, and I know that's 130 meters. The long side of the ground measures 100 meters. Okay, there's 100 meters. Thank you very much. And find the length of the shortest side, which would give us this side here. And I know that it's a rectangle, and rectangles have a right angle in that corner. And so I can write down that c squared equals a squared plus b squared. Have they given me the hypotenuse? Yes, they have. It's 130. So that's 130 squared is equal to, well, let's call that x. So we have 100 squared plus x squared, and I'm just going to dive straight into my calculator to allow that to solve it for me. Let's clear down what's already there so we don't get confused, and hit the solve. 130 squared is equal to 100 squared plus x squared. Close the brackets, put x this time because I want to solve for x, and that gives me minus 83 we don't care, and 83 we care about. Now, this is a trick of the question because they try and trick you with the units. So here we could write down then that x was equal to 83.06623.863 in meters. The question doesn't want it in meters, it actually wants it to the nearest centimeter, and there are obviously 2 things we can do here. We could multiply that answer by 100 because it's in meters. So we could say that x was equal to 8306.623863 in centimeters, but it wants it to the nearest meter, the nearest centimeter, which would give me 8307 centimeters. That's certainly one way of doing it. Or we would know that to be able to round to the nearest centimeter when it's given in meters, that's actually just trick to say round it to 2 decimal places. So rounding that to 2 decimal places, I could also say that x was equal to 83.07 meters. And both of those answers are absolutely acceptable. Well, there we go, ladies and gentlemen. That is our sojourn, our quick flick through Pythagoras' Theorem. Thank you very much for watching. Again, if you haven't already done so, head over to mathsguru.com where you can get all of these videos. You've got notifications for new videos and all that exciting stuff. Searchable, time codes, downloadable resources, exam questions, you name it, it's over there. But otherwise, I'm done. Thank you very much for watching this video. It's been good to see you. I look forward to seeing you next time. Take care. Have a good day.